Hi everyone, welcome back to all of you on my YouTube channel. I'm Ankit Mishra. I'm teaching for GATE Chemical Engineering since last 5 years. So obviously you can see I have started the lecture series of process science and control, and where I have describing all of these fundamental concept that is related to GATE as well as the bar examination. And this lecture is going to be very helpful for the person who is appearing for the interview for NPCL 2025 also. So in the previous lecture, in lecture number 6, I have described about the transfer function of continuously stirred tank reactor, where I have assumed there was a first order reaction in which reactant A was getting converted into product B with rate constant K, and I have assumed the isothermal condition where inlet volumetric flow rate of the reactant was V naught, and inlet concentration of reactant was Ca naught, and final concentration at the exit of the reactor was Ca. I have assumed the volume of the reactor was V, and from here you can see that we can write the rate expression is minus R equals to Kca, and we want to find out the dynamics of the CSTR, means concentration profile, something like that. So if you do the material balance, then you can write rate of in minus rate of out minus consumption, that is equals to accumulation. This is the fundamental concept of chemical reaction engineering for mass balance system. So once we apply the mass balance, you can see there is dynamics associated with that, means concentration of the reactants and the time. And now if we again rearrange this particular thing, you will be getting this thing. So I have assumed the space time of the reactor tau is equals to V divided by V naught, right? And after that you can see we have got the equation first, where in terms of ordinary differential equation, your dCA divided by dt, that is equals to plus Ca into 1 by tau plus K equals to Ca naught by tau. Now I have already described in my lecture number 2 for process science control how to solve this ordinary differential equation while taking a Laplace. So once I take the Laplace transform of equation, first you will be getting these things while subjecting the initial condition. Initial concentration Ca inside the reactor will be 0 at any particular time, t equals to 0. So finally you will be left with equation number 2, and we know the transfer function is the concentration of the reactant at the outlet and divided by concentration of the reactant at the inlet, Ca by Ca naught. And the equation third, which is the transfer function of the continuously stirred tank reactor. So either you want to write in terms of tau, that is in terms of space time, or you can also do some modification or simplification to get the equation number 4. This is the final equation of the transfer function or final transfer function. So here Ca is the response, means output concentration, and Ca outlet concentration, and Ca naught is the inlet concentration. So let's see if I am giving a strip input of magnitude m here, that I have already described in my earlier lecture. So after that we can solve this equation while using the inverse Laplace transform, and this can be solved while using the partial fraction thing that already I have discussed in my lecture number 2. If you will go there, you will get all of these kind of methods, that how to solve this partial fraction, and after that how to take the inverse Laplace, right? So all of these lectures are very important. Again, if I talk this concept, this concept has been asked in GATE 2025. So again you can see based on the material balance, questions are coming every year, so that is very important. So today in this lecture I will be going to talk about the transfer function of a plug flow reactor. So plug flow reactor, very rarely people solve on YouTube or on anywhere else. That's why I came up with the concept. Okay, if in future if they put a hypothetical question on plug flow reactor, then how can you approach, right? So let's just start with transfer function for So here in plug flow reactor, what we see, the concentration vary along the length of the plug flow reactor, something like that. Okay, so let's say this one is the plug flow reactor, so the reactant will in here and it will be coming out here, right? So here if reactant is Ca naught, and here concentration is at the exit is Ca, so this particular length will be Z equals to 0, and this is the Z equals to L, right? And if I am measuring volume of plug flow reactor is V, so again if volumetric flow rate at the inlet is V naught, and at the exit again I am considering the volumetric flow rate will be V naught. So first I will derive the value of tau, that is the space time for plug flow reactor, that is tau, that is equals to V divided by V naught, means volume of plug flow reactor divided by volumetric flow rate. This is Z equals to 0, Z equals to L, and again I am assuming that the first order reaction for first order reaction system, if a reaction A is getting converted to B having n equals to 1k, so I can write minus of Ra that is equals to KCA. So since why I am taking the first order reaction, because it is very linear, right? Simplistic case. If you will take second order and nth order reaction, then you have to linearize this while using the Taylor series expansion that we'll see in the later section of next to next lecture, and there you will see how to linearize a non-linear function in for taking the Laplace, right? After that, if I do the material balance, uh, how can I write the material balance for this? So here this can be written as directly, if I write del CA divided by del T plus U del CA by del Z, that is equals to minus KCA, right? This one is, let's say, my equation first. Okay, so where U is the velocity and K is the rate constant, and C is the concentration at any particular condition. Now if I take this taking Laplace of equation first, if I'll take Laplace of equation first, what I can write, Laplace of del CA by del T plus Laplace of U del CA by del Z, that is equals to minus K Laplace of CA, right? So if I take the Laplace thing, so S into CA at ZS, because concentration is going to vary along the length of the PFR. So now you will be getting del U del CA, and it will be S and Z divided by del Z, that is equals to minus K CA SZ. Why I am writing these things? Because see, the question has not been asked till now on the plug flow reactor, but let's see if somehow if they will make some kind of this kind of question, and they will ask you an MCQ question. So they will put the options and they will ask you which of the following options are correct for the for deriving the transfer function for PFR. So you should know these things. But now again you can see there is a ordinary differential in terms of Z, right? So we don't want this kind of differential here. So what will I do? So I'll write del CA SZ with respect to del Z, and plus, again you can say, or directly I'll say I'll send all of these terms that side, so minus, and this is CAZ, so I can write K plus S CASZ. Okay, now this is just ordinary differential equation also in terms of Z, so directly we can solve these things. So let's see, if I will assume this one is the equation second, so if we solve these things, what I can write directly CASZ, that will be equals to minus K plus S and CA in terms of so del CASZ divided by CASZ, that will be equals to minus K plus S del Z. And if I integrate these things, so while integrating, what will I get? Let's say 0 to CA and 0 to L. Is that clear? Or 0 to Z I am assuming right now at any particular location. So this will be ln CASZ, and that is 0 to CA at Z, that will be equals to minus K plus S into Z. So finally we want to calculate the value CA of SZ, that is equals to exponential, you can say, minus K plus S into Z. Is that clear? I think I have written one mistake, that I have to divide with my U also. So here U have been left something like, okay. So this one is the thing. So let's say if you want to calculate the outlet concentration at L, means Z equals to L. So how can we write these things? So directly we will go CA SL, that is equals to exponential minus k plus s divided by u into L. So this is how you can derive this transfer function for the plug flow reactor at any particular location. But if you want to get the final transfer function here, so here I think I'll not start with CA, it will be CA node only, so that would be fine I think. So ln CA node, something like that. So this will be your CA node SZ, right? So again CA divided by CA node SL. Now, so what is transfer function? So the transfer function will be equals to CA at SL divided by CA node at SL. That will be equals to your exponential minus k plus s divided by u into L. So this will be your final transfer function for plug flow reactor. So I think and there is a confusion in solving this kind of a transfer function for plug flow reactor. Why I am telling you these things? The reason is that because here you will see two kind of differentials are there with respect to time and with respect to space. So with respect to time, you can take the Laplace and you can convert this into S domain. And once you take this in S domain, but again you are not you won't be able to take this in terms of T domain. Why? After taking the Laplace inverse, because these kind of issues are happening here, right? So again, if you want, you can convert this into this domain also, because there is exponential and then this term will be there. So CA naught is kind of input, so this one is your input. So what kind of input you are giving to the plug flow reactor at the inlet, and based on that input again you have to take this Laplace inverse for CASL, where CASL, CA is in S domain now, so it will get converted into T domain. And if you want to convert this into T domain, you have to take the Laplace inverse. And once you take the Laplace inverse, again the concentration profile you will get in terms of time, and that will tell you the dynamics of the plug flow reactor at any particular location or at any particular time, something like that. So with respect to both space and time, here the concentration is varying, right? Why I am telling you this thing? So let's say it can be possible at any particular location z equals to, let's say, L1, L2, L3, or sorry, I'll be writing z equals to Z1, Z2, Z3, and this is z equals to L. So at this particular location, concentration will be different. Here concentration will be different. Here concentration will be different. And at any particular time, T1, T2, T3. So at every location, you will see, if I write T1, T2, T3, T4, and here it should be Z1, Z2, Z3, right? So with respect to T1, concentration at Z1, Z2, Z3 will be different. At with respect to T2, Z1, Z2, Z3, that will be different, and here it will be different, something like that, right? So that's why you can see that concentration is a function of both space and time in plug flow reactor. Why? Because along the length of direction the concentration is changing. That's why you have to solve for Laplace when you will convert these things into S domain, and once you convert this into S domain, again you are left with a differential that is in terms of Z, and again you will solve this differential in terms of Z, and then you will be getting this kind of equation, right? So this is the transfer function in terms of S domain now, right? So this is the transfer function for plug flow reactor, PFR, right? And once you get this transfer function, now you have to solve this for your T domain. And how can you solve this for T domain? You can take the inverse Laplace, and after taking the inverse Laplace, again you can solve these things. Okay, I hope this is clear to all of you. I'll stop this lecture up to here only. So those who have not subscribed my channel, please go and subscribe the channel, and don't forget to press the bell icon, so that if I'm putting the new video, definitely you'll be getting the notification, and you can see the impact of these kind of lecture when you will start watching all of these my lectures. So definitely you'll be getting huge benefit, as well as the BARC examination and another state examinations also. So and also, I mean, when you are going to the for BARC interview and nuclear NPCL interview, all of these interviews also, so they will ask you this kind of fundamental thing, whether you are able to apply the mass balance or not, and after applying the mass balance, whether you are able to apply the Laplace transform or not. So ultimately what we are doing here, so while using the Laplace transform only, we are converting the ordinary differential equation to uh, we are solving the ordinary differential equation, and after that we are getting the dynamics. Okay, and in the next lecture I'll be talking about the transfer function of tanks and interacting and non-interacting. Okay, thank you, see you in the next lecture.